Good morning, everybody, and welcome to the last lecture before our first exam. This material will not be on exam 1, as I said before, but that way you have a little more time to digest the material for exam 1. So that's why we ended with the material last week. I hope all of you have gotten a little more familiar with it through the homeworks. And of course we will be doing some review playing Jeopardy the next 2 classes. So that will hopefully clarify a lot of issues. I assume everybody got the email. There was a mistake in the last lecture in the derivation. Phi is defined as 2 pi hx plus ky plus lz. So the fact that I wrote e to the I 2 pi phi was kind of a double on the 2 pi. So just erase the 2 pi in the exponent of the e function whenever I wrote phi. Okay? I think it's like 2 lines where you have to erase it. Now, we've talked a little bit about this before, about Fourier transforms. We had some functions up that we said are Fourier transforms. But given that all of diffraction is based on Fourier transforms, we really need to spend a little more time trying to understand what that means, both for our diffraction data and for how we analyze our diffraction data. So let's take a step back and let's talk again about the electron density. That's what we are after, right? We want to analyze the electron density in the crystal. For that matter, we really care about it in 1 unit cell, but we are making use of the fact that we could describe the electron density of a crystal as a periodic function, and that is what causes our diffraction, right? We have the same contents in each unit cell, and that means that the electron density repeats with the unit cell repeat. And we've learned by now that we can use some kind of sum of sine and cosine functions to actually describe this one. Now here's something that takes some paying attention to. The wavelength is related to the lattice periodicity. This is not like our X-rays, where we just select one wavelength and we shoot one wavelength X-rays at our crystal. This electron density function is actually related to the lattice periodicity. So it'll be different for every crystal. Okay? Now let's introduce a few more terms that are useful when you deal with Fourier transforms. And that is the terms Fourier synthesis and Fourier analysis. Basically, if you take a periodic array of anything and you describe it by the sum of cosine and sine waves, you get what you call a Fourier synthesis. So you take a whole bunch of individual waves, you sum them all up, and you get a periodic function out. That is called a Fourier synthesis. The same way, the opposite, if you take some periodic function and you extract those individual sine and cosine waves from it, you call that a Fourier analysis. And here's a very simple picture of this for 2 waves. Okay, here are 2 individual waves. If you add them up, you end up with this one. Okay, you cannot describe this function very easily by a single sine or cosine function. It's still a periodic function, right? It has a repeat, but you actually need 2 different waves to describe it. You can't just use one wave. So these summed functions can look a lot more complex than a sine or cosine function. Okay, you have different heights of some of these peaks. You don't have a maximum followed by a minimum. And that's just because some of these incoming waves here could have different periodicity. Okay? So this step is the Fourier synthesis. Take the waves, sum them up. Alternatively, you could take this one and try to extract these individual waves out of it. That is a Fourier analysis. Okay? Now, what does that have to do with diffraction? A heck of a lot. Let's introduce one more term, a Fourier series. If you have a complete set of waves that you need to describe some periodic function, that is called a Fourier series. Okay? The emphasis here is on a complete set. And this relates directly to our diffraction, because if you think back to the intensity of a Bragg reflection, that one was somehow related to a summation of things, wasn't it? Because it is related to the F, to the structure factor. So it is related to the amplitude of an electron density wave in the crystal in the HKL direction. And that is a strange concept for us, okay? Because when we think about waves, we think about light, we think about X-rays. We don't necessarily think about something like an electron density wave in a crystal, okay? But if you look through the crystal in a certain direction, you could describe the electron density by some kind of a wave function, okay? You see more, you see less, you see more, you see less. Now, if you collect all of your Bragg peaks for a crystal, you would have a Fourier series that describes your electron density, right? You have every single perspective, every single wave that contributes. So, that would be a Fourier synthesis if you take all those Bragg peaks to make up your electron density, right? You can also describe the scattering of X-rays by atoms as a Fourier analysis. Basically, you have this full periodic array of electron density, and what you get are these different Bragg peaks, the different electron density waves in different directions of the crystal. How can we actually express this? Well, here's our electron density. Okay, our electron density would be related to our structure factor magnitudes. We talked about those last week. You sum over all HKL values, and of course you have to normalize for the volume. And because this is the magnitude, we still need to have this E function in there, right? If we had written a vector here, we could kind of save ourselves that one. We just put an arbitrary phase shift in here because we haven't determined our origin when we talk about our electron density here, right? So, this is certainly a Fourier synthesis. You take all of these individual waves. Here's our sine and cosine hidden, right? And we sum them all up. And we get a periodic function out. Now, what do we need to keep in mind? Here's an example of some of these electron density waves. Remember how we drew those lattice planes from Miller indices? Well, they kind of correspond to planes that represent, for example, the maximum of a wave, okay? Here are some of them. They can look pretty simple or pretty odd, depending on what our direction is. The most important thing to remember is each one of these has a different wavelength. Okay? That is something that is very easy to forget, because we shoot monochromatic X-rays at the crystal in most cases, right? So we are so used to work with one wavelength. Like when we deal with Bragg's law, lambda, we have to plug a number in, but we assume it's one constant number. All of these waves have different wavelengths. Okay? So it's no longer quite as easy to look at constructive and destructive interference as it was for our X-rays, right? Because we no longer have the same wavelength. So we can't do all of these nice little manipulations where everything drops out. Now, if we really want to get the electron density, we would need to sum over all possible waves. What do you think our chances of that are? Christy says we don't stand a chance. Does everybody agree? Let's see. How many HKL values would we have? Is there a limit on what the numbers of HK and L can be? No, right? So we have an infinite number of HKLs, kind of. What's your chance of measuring an infinite number of reflections? Even if it was physically possible, given that you at some point in time want to graduate, not good, right? Because it would take an infinite amount of time. Part of it is you will just run out of reflections that are strong enough to detect them, okay? So there will always be limitations. We'll be getting back to that quite a bit, because that introduces something that we call truncation errors. Now, here's another example for summing electron density waves, okay? This one is a one-dimensional example. There are some atoms sitting here in each unit cell, okay? 2 atoms in each unit cell. And they drew the 100 reflection, the 200, and the 300. So what happens is you have these parallel lattice planes, right? Spaced d100 apart. You have the parallel lattice planes here, which are spaced d200 apart, which is 1/2 d100. And you have the parallel lattice planes that are spaced d300 apart, which is 1/3 of d100. Okay? And I kind of indicated here with some of these dotted lines where these things would be. Here you have these waves. Here you have twice as many waves. Here you have 3 times as many waves. And so you can then look at this density wave. Here's your periodicity, okay, for the 100 wave. Your 200 wave, periodicity is half as long. 300 wave, wavelength is 1/3, okay. In this example, they drew all of them with the same maximum intensity, okay. If you sum these 3 up, we end up with this one down here. It's a periodic function, okay? It's not one simple sine or cosine function, but it's a periodic function. Now, if you look at this, you have 2 peaks fairly close together, then you have a slightly larger gap, then you have another 2 peaks, slightly larger gap. That is really what it looks up here, right? You have 2 atoms, and you have a gap, 2 atoms, and you have a small gap. Because these black dots here, that's the atoms. Okay? So, in this case, just summing these 3 waves actually gives you some kind of idea in that one-dimensional example how these atoms are arranged. Okay? Now, in a perfect world, what do we know about electron density? Should it be positive, 0, negative, any or all of the above, only some of the above? Can we have positive electron density? We can have a certain amount of electron density on somewhere, right? That's okay. So we can have. It's not a positive charge, okay? If I say positive electron density, it doesn't mean positive charge. It means a positive number of electrons in that volume element. Can we have no electron density? In absolute vacuum, yeah, right? We could. Can we have negative electron density? Anybody ever seen -1 electron? So that doesn't work, right? So if you look at this, you can see that this isn't really completely correct because there are some negative areas left, right? Remember how I said we would need an infinite number of reflections to have a complete Fourier series? We don't have an infinite number, we have 3, okay? So this is what we call these truncation errors. You will have some negative numbers there, although we know they're physically meaningless, okay? It's simply an artifact of the fact that we only have a limited amount of data. Now, that's for 3 waves, okay? And it's a pretty simple example, and it's certainly not a real-life example. Here's another example. And this one actually is a more realistic example, okay? Once again, a one-dimensional Fourier synthesis. Here's your 0, 0, 0. It really doesn't have periodicity, right? It's just some generic incident intensity that depends on what kind of atom you have. And we have the 1, 0, 0 wave. Only one wavelength. The 2, 0, 0, the 3, 0, 0, and so on. And what you can see here is, first of all, we have very different intensities of these waves, right? So as I said, this is a more realistic example where the different structure factors would have different magnitudes. The other thing that you see is that we have some phase changes here, right? Some of them start in the negative, some of them start in the positive. And if you take these waves up to the 1000 wave, you can start summing them up stepwise. If you only have the 100 wave, this is what you get. that useful for figuring out where your atoms are? Not really, right? If you sum up to the 200 wave, I still wouldn't want to assign atoms there. Anybody want to give a comment about where you might be confident about assigning atom positions? Everybody pick a number. Don't have to say it out loud. Pick one in your head, okay? Look at all of these things and think about at what of these numbers would I be comfortable to say, I think there might be an atom here. So, seems that most people are somewhere in this range for that, right? 6 or 7. Part of that is a little bit, you know, some people are a little more picky. Some people have a little more courage to just go ahead, assign something, and take back the mistake if they make one. I would agree. Somewhere, one of these, that is where it starts to look like we can see atoms. 500, it's really not very good yet, right? We have a dip here that is almost as high or as low as these mountains are. Not so good. This is the first one where we kind of see some flattening out in the middle. And this is where we certainly see that this is flattening out because we get an additional little hill there, right? So, somewhere around here we would be confident to assign atoms, and if we sum to 1000, it just gets even more clean cut, right? So, while we theoretically need an infinite amount of reflections, in real life, if you have a decent number of reflections, you can usually assign your atoms. Okay, now this is a one-dimensional example. So we can live with some 6 to 10 reflections. Okay, of course in 3 dimensions and with more than 2 atoms, life gets a bit more complex. So don't ever measure only 10 reflections and think you can solve your crystal structure from it. It's not going to work. But you will be able to live with a finite number of reflections. So, everything we are doing is based on Fourier transforms. Okay? Here's the generic definition of a Fourier transform, because most of us really haven't done too much work with these before we encounter them. In crystallography or a similar class, right? Fourier transform basically relates two periodic functions that depend on different variables. Okay? Here's a function of x, and this x could of course be, you know, more than just one variable. It could be x, y, z, for example. Here's another function, g of y. Different variables. We form an integral from minus to plus infinity. We throw in an e function, a complex e function that has both variables in. Okay, that is one of those distinguishing things about a Fourier transform. This e to the I2 pi, first variable times second variable. And if the integral is over g of y, of course we have to say dy. Alternatively, if we take the inverse Fourier transform, all that changes is we have f of x dx here, and if we really go directly from here to there, in order to make it inverse, we have to change the sign here. Okay? These are a Fourier transform and the inverse Fourier transform. And life can get more complex. Okay, you can have convolutions of Fourier transforms, which you write with this strange symbol, cross in a circle. That's a convolution of two Fourier transforms. If you have a convolution, you once again have an integral, and you have f of x, and you look at g around x, basically, okay, if you think about it. So it's this x minus x prime. So it's somewhere at a similar place, but it is, you know, not right on the same place. So it's kind of defining an overlap between two functions. That is what this really is. It's looking at how do these two functions overlap or interact, or how do they blend with one another. Okay? And luckily for us, most of the time, we just leave it to the computer to do these calculations. Okay? And the computer knows how to handle a Fourier transform. Isn't that nice? Now, let's get back to what we were just talking about, structure factors and electron density, right? We have shown, that our structure factors are really a Fourier synthesis of waves scattered by a crystal, right? Remember? Our F was a sum over all HKLs. So basically our diffraction pattern is nothing but a Fourier transform of an object. And in our case, the object is a crystal, okay? So we Fourier transform our object, our crystal, and we get our diffraction pattern. And because of the periodic nature of the crystal, we get a diffraction pattern that has spots. Otherwise we wouldn't get spots, okay? So those of you who might be working with other types of X-ray experiments, you will not always get the periodic array of structure factors, okay? But you still get a Fourier transform of your object. These basic rules still apply. Now the other thing that we have shown is that we can obtain the electron density from a Fourier synthesis of all of the electron density waves or structure factors. And that means that if we do an inverse Fourier transform of our diffraction pattern, we get our original object again. Okay? Because if you do a Fourier transform and an inverse Fourier transform, if you look at how they are defined, if you apply one after the other, you get back your original function. Okay? And that is why these Fourier transforms are so important. Because what we usually measure are the structure factors. If we apply that inverse Fourier transform, we get back what we were originally after, which is, what does our crystal look like? Okay? Most of the time we are going after what does the inside of the crystal look like, what is the periodic array of electron density function. If you do small angle scattering, you're more interested in what do our particles look like. Okay? As I said, in that case you don't have the periodicity superimposed, but you still have a Fourier transform. Okay, so you will be using this whenever you analyze your X-ray data. And here's our relationship. Okay, FHKL is equal to the integral of e to the I2 pi hx plus ky plus lz times the density of rho xyz dv. This is what I mean by that f of x and g of y can be more than one variable. F depends on three variables, h, k, and l. Okay? Rho depends on three variables, x, y, z. The three of them together give you volume, and that is why we integrate over all volume. Okay? And here's that e function. E to the I2 pi xy is what I wrote on that Fourier transform definition slide, right? And here we just have the hx plus ky plus lz. That's the two sets of variables, hkl and the xyz. And alternatively, we can get the electron density by the inverse Fourier transform of our structure factors. And this is reciprocal volume when you use a small letter v, okay, which is related to real volume with the reciprocal relationship. Kind of no longer that surprising, right? We've dealt with reciprocal lattice constants. So here are your Fourier transforms on which your diffraction experiment is based and your data analysis is based. Now, let's have a slightly more graphical look at these things. What's that relationship between f and rho? Well, we know that part of f is, we know how f is defined, capital F, right? Was the sum of all fj, small fj, times e to the I phi j. Remember? So we had this little f, the atomic structure factors, the atomic scattering factors in there. And that one actually is directly related, well, directly, Fourier transform related, so not really a simple multiplication relationship with the atomic density, okay? Your atomic scattering factor is related with the atomic density, electron density. Now, we know what the atomic electron density approximately looks like, right? We learned that in general chemistry. Here's our s orbital. The 1s is at a smaller distance than a 2s. 3s is a little more stretched out. Then we have these p orbitals, which kind of show a little bit of tailing. So that's our orbital shapes. If you take whatever orbitals contribute to the electron density of an atom and you Fourier transform them, you get these atomic scattering factors. Okay? And here's a drawing of what that looks like. The 1s, which is close to being a point, right, is a fairly constant function with sine theta over lambda. The 2s does drop off a little bit because it has a certain magnitude, okay. The 3s drops off a lot more quickly. The p orbitals kind of drop off, they have some curvature to them. And what you then do is, depending on your atom, you just sum over all the orbitals that contribute. And so you usually get some kind of a function like this one out, okay. It starts at an f, that is the maximum number of electrons, and then it starts dropping off. And of course your p orbitals start higher than your s orbitals because we have 3 p orbitals and only 1 s orbital, right? So there are more electrons in the p orbitals if they're completely filled. So this is where this strange value of f comes from that we kind of just introduced as how effectively an atom scatters X-rays. This is the Fourier transform of your orbitals in which the electrons are. So back to something that I think we had up before. And that time we couldn't quite understand all of it. Fourier transforms in crystals, okay? You have a crystal structure, and it could be described by an electron density with x, y, and z values. What you measure is a diffraction pattern, which gives you these FHKL values. Right? The two of them are related by a Fourier transform. But now comes the point where I actually had to introduce those convolutions. While we don't mathematically usually do them by hand, what your crystal is made up of is the contents of one unit cell and the lattice periodicity. Okay? That is what we would call a convolution. We have two portions of it. And the crystal lattice is related by a Fourier transform to the reciprocal lattice. Remember, that was the first time we talked about Fourier transforms, when we introduced the reciprocal lattice. The unit cell contents are related by a Fourier transform to the diffraction pattern of a unit cell, okay, which would be a molecular transform. And you hardly ever work with that, because let's check in real life, how many chances do you have to have a single unit cell at which you can shoot X-rays? Not so good, right? Doesn't work too well. If you work with really big molecular compounds, you may stand a slightly better chance to get something similar to this, because you could do a Fourier transform of your molecules in solution, right? And that is actually, in some cases, what the protein people do when they do small angle scattering, okay? So there you can actually kind of get into this realm. Now, what do we observe? Do we simply observe the straight reciprocal lattice? No, right? We can do exercises with that, we can draw it, we can calculate it, but what we measure is these FHKL values. And the reciprocal lattice doesn't have any intensity differences, it just describes where we can see diffraction. This is what superimposes some kind of an intensity function on this, okay? This is what determines which of these spots has how much intensity. And so what we measure is this. As we said, if we have a convolution over here in the Fourier transform, what that means is that we multiply the two functions. And that is what is so convenient. We can deal with that reciprocal lattice, we can get to it pretty easily, and then we multiply it with some kind of intensity function, and that is what we get out. So, very important that we deal with Fourier transforms, because that is what all of crystallography is based on. There are actually more convolutions, okay? And this is mainly to warn you. There are more things to consider. So sometimes, if you can't quite explain what you see, you may have to think about your experimental setup, okay? Your slits confine the X-rays, right? What does that mean? Can we get diffraction from the slits? Based on how we came up with the whole concept of diffraction, how we derive Bragg's law, yeah, absolutely, right? So there's another convolution. So the instrumental setup will determine how exactly your data looks. Now luckily, usually you have a computer hooked up to your instrument that knows something about your instrumental setup, okay? Or if you work with certain programs, you can tell them something about your experimental setup. But these are things to keep in mind. So you get a so-called envelope function, which has something to do with what your slit setup is, okay? This will determine how your data look. If you change your slits, your data resolution will change a little bit, okay? And this is something that you will learn once you actually do experiments. For what kind of experiment do I use what kind of setup? But keep in mind that your setup will actually influence what your data looks like, okay? So if you don't get ideal looking data, don't immediately say, oh, this is all nonsense. Think about, can I actually do something to improve it? And of course, in most cases, you walk up to an instrument that has a setup that works for many people. But if you go somewhere and you find a diffractometer sitting in a corner that nobody has touched in 10 years, maybe it's not the ideal setup, okay? So here's a closer look at that envelope function. How does it come about? Why do slits actually influence this? Well, if X-rays go through a slit, they will kind of spread out behind the slit, right? Diffraction at the edges of an opaque body. I think that was one of those early definitions of what diffraction meant. And basically, when they start going out, we will have X-rays that are slightly out of phase with our straight beam of X-rays. And the further you go out, the more they are out of phase. And that is where we kind of get this drop off, okay? The wider your slit is, the more they can go out. And that means the quicker they go out of phase. So that is where this envelope function comes from. Once again, it's a reciprocal relationship. The wider your slit is, the narrower your profile of that envelope function, okay? Now, here's another nice little brain exercise. Diffraction from holes. Let's look at this from a Fourier transform perspective, okay? We know what diffraction from a single hole looks like, right? We get a ring pattern. And depending on how big that hole is, we may get one single ring that is kind of diffuse, or we may actually get multiple rings. We have a nice narrow hole. Alright, so we get a ring pattern. What happens now if we have a second hole, same shape, same size, at a certain distance from it? It's called the distance A, okay? Now we go back to that general scattering equation that we derived. As I said, you don't need to know the derivation, but the outcome is important. So for one hole, we can give the scattering equation, right? We'll call it A0 because this is our first hole of the scattering vector. So the amplitude of the scattering is equal to the integral over E I to the 2 pi SR times rho of R dVr. That's the equation we arrived at. Now if we have two holes, Basically we get scattering from one hole and we get scattering from the other hole, right? No magic done here. So we'll just sum them. And our second hole is of course not at R, it is at R plus A, right? So there's our big change in the scattering function for the second hole. And here's the scattering function of everything. Now this kind of goes back to some of the mathematical cosmetics that we did when we looked at systematic absences. I have an E function of a sum. E to A plus B is equal to E to the power of A times E to the power of B. Okay? If we apply that here, and we have a common factor E to the I2 pi SR, both here and here, multiplied by rho of R dVr, and we are left with another factor E to the I2 pi SA, right? Does that one still depend on V? E to the I2 pi SA? Does it depend on the volume? Does it? Not really, right? This is one distance between two holes. So, that one really doesn't need to be in the integral. The R of rho of R dVr has to be in the integral. But A is just one specific vector. So, we can say we already know this was, the one was A0S, right? So we write that A of S is equal to A0 of S times 1 plus E to the I2 pi SA. Does that kind of function look somehow familiar as of last week? Or as of the homework? Yeah, right? The sum of a number and a complex E function. So, we can already tell that A of S will have places where there's extinction, right? Because we know that we can represent this one as a sum of cosine and sine. We know the sine is going to drop out because S times A has to be certain numbers. And so what we see here is that this second hole will really superimpose something that we can call a fringe function, okay? It will superimpose a wave function onto this first pattern. Sometimes we will double the amplitude. Okay, this function could become 1. So we would have 2 times A0. Sometimes this function will be minus 1. In that case we'll have extinction. Okay? So that's what the second hole does. So whenever A times S is integral, we'll get doubling of the amplitude. Halfway in between, we will see no intensity. This is what that will look like, okay? Here's a diffraction pattern of one hole. Here's the diffraction pattern of 2 holes separated by a certain distance. It puts a fringe function on, okay? It's probably not what you would have expected if you have never looked at any of this math, is it? But having gone through the math, you can explain that this indeed makes sense, okay? So, pretty impressive what the second hole does. But of course the question that you might be asking is, what the heck has a hole got to do with a crystal, right? And it's all nice and good that I talk about math and about holes and Lord knows what. Who cares? Well, so the hole scattered the light rays. The same way we know that an electron scatters X-rays. So, just imagine that a crystal is a hole pattern of electrons. And you get a good analogy of what is happening in a crystal, okay? Here are some examples. These are obviously pieces of paper where somebody just punched in a hole pattern, okay? I'll admit that. But if we assume that each of these holes is an atom with a certain number of electrons, then the same thing should happen if we shoot X-rays at the atoms that will happen when we shoot light at these hole patterns, right? And that's indeed true. Because remember, both light and X-rays are electromagnetic radiation. So all we need is something that scatters the electromagnetic radiation. A hole will scatter light. An atom with electrons will scatter X-rays. So, it'll be a nice analogy. And this actually allows us to look at some of those molecular transforms that we just talked about. Because I can punch out a single molecule on a piece of paper. It's not a problem, right? So, here's the diffraction pattern you get from part A. It's a periodic array of atoms, right? Two-dimensional periodic array. What do you get? A two-dimensional periodic array of diffraction density, right? Diffraction intensity. And once again, here in real space, we have a shorter distance along this direction, a longer distance along this direction. What do we see over here? The shorter distance is at 90 degrees to the original. The longer distance is in this direction. Okay? So once again, it's reciprocal space. It's an inverse relationship. Alright. How about B? That should be a molecular transform, right? That looks like a benzene ring or something like that. We left the hydrogens off, but so be it. This is what the diffraction pattern would look like, okay? This is not what a crystallographer would immediately call a diffraction pattern, but this is the molecular transform, okay? Molecular Fourier transform. So there's one benzene. What do you think will happen if we put a second benzene there? There will be some kind of overlap between the two functions, right? So we'll still have something that arises from the molecular transform. We never completely lose that, but we'll superimpose a fringe pattern, right? That's what should happen, according to what we derived for a hole. Now instead of one hole, we have basically a set of holes, right? But once again, we have the same thing at a certain distance. So let's see what happens. That's exactly what happens, okay? We take this one and we superimpose a fringe function onto this one. I guess figuring out what D should do is not that difficult, is it? We'll superimpose a fringe function in this direction. There it is. Now notice, this only has a 2 times periodicity in each direction. It's a pretty dramatic change, isn't it? What happens if we make it a long line? Well, the fringe function just will become more clear-cut, okay? This is in one direction, this is in both dimensions. Does that look about like what we usually see as a diffraction pattern? So that's how the diffraction pattern comes about, okay? You have a molecular transform or a unit cell transform if you don't work with molecules, okay? It doesn't matter which one it is. And you superimpose these fringe functions, which is what gives you your reciprocal lattice, okay? Because remember, we multiply 2 Fourier transforms. We multiply the reciprocal lattice with the intensity function. That means if the reciprocal lattice says somewhere there is no intensity, whatever was there originally in the molecular transform will be no intensity, because 0 times something is always 0. So the reciprocal lattice really comes from this fringe function that is superimposed in that scattering equation if we have more than one object. And that is what makes for these pretty looking diffraction patterns, okay? I'd much rather work with something like this than with something like that. Part of that might just be that I've happened to work with something like that a lot more, you know. But this is what you will usually measure, because your crystal will have periodicity. So, that's what a hole has to do with a crystal. We can make a direct analogy there. Now, usually you don't start changing your crystal around, right? What you do is you collect data in reciprocal space, and then you have to go back from your data, do an inverse Fourier transform, and figure out what your crystal looked like, right? So let's have a look at what happens when you try to transform your diffraction pattern into an electron density map. The opposite approach, okay? So let's start with something. We were really lazy, or really pressed for time, or maybe we had a really crappy crystal, didn't scatter too well. So we measured 4 reflections. What do you think? Are 4 reflections going to be good? We've all heard the word infinite number should be for a full Fourier series, so we say no, shouldn't be good. Here's the electron density that you get from a Fourier transform of this. Anybody want to assign atoms to this one? Probably not, right? So, let's measure a little bit more. I know this is still only 6 reflections, but it's a factor of 1.5 more than this, right? Here's what you get. Anybody want to assign atoms? Probably not, right? Now the other thing that you notice here is things are completely changing, aren't they? So obviously whatever amount of reflections we have so far really doesn't give us anything realistic, or things shouldn't be changing around this much, right? Now, what's one of the things that we are missing here? One of the things we are missing is the F000, which kind of scales things. Okay? What does that do? That makes a huge difference, doesn't it? All we measured between here and there was the F000. Now this is the first time that I have something that looks like there's something connected in here. I still wouldn't want to assign atoms there, don't get me wrong, okay? But this looks a heck of a lot more like there might actually be some kind of molecule in there than any of these, right? F000 is quite important. One of the things you will find when you do single crystal diffraction is that the program asks you, what are your unit cell contents, okay? It asks you because your unit cell contents give you the scale for that one, right? Because the maximum scattering efficiency of each atom is what? The number of its electrons. So if you know the total number of electrons in your unit cell, you can scale your diffraction data, okay? You don't know your total number, you can't properly scale things. So that's why you really need to know what your F000 should be. Now let's measure a few more. That looks a bit more realistic, right? That looks like somebody actually measured some diffraction data. This is what you get. Does that look more reasonable too? Getting individual atoms may still not be very easy, okay? But at least this looks like there is something that has some connectivity. Well, let's measure a little more. This is certainly a lot better, okay? That starts to look like something where if we have some idea from NMR what this molecule might look like, there seem to be some rings here, you know, there's some kind of central ring system. We might be able to assign something here. Does everybody agree? It may still not be as nice and pretty as you would like it, okay? But you could probably start assigning some atoms here. And this is actually what the calculated electron density from a model looks like for this molecule, okay? So this pattern really doesn't look that different from what you get here. Okay, so yes, you could assign atoms there. Now, What is the lesson that this one teaches us? We need a lot of reflections, yes. Now, you might have heard people talk about d-spacings and resolution of diffraction patterns. If you've ever sat in a crystallographic talk, be that in a group meeting, be that in a seminar, you probably heard people say, oh, and this crystal is scattered to that and that resolution, right? It's one of those things where you wonder, what the heck are they talking about? This is what they are talking about, okay? How far out you measure your reflections determines how good your electron density map is, okay? So, the larger your D star, right? Because that's the further out we measure. D star is measured from the central point here. The better the resolution of our electron density map. And because usually when we talk about resolution, we talk about electron density maps, okay? Resolution is usually given with a D spacing attached to it. Now, we've learned how to convert D star to D, right? How do we do that? 1 over D is equal to D star, or D is equal to 1 over D star. So you can give a D spacing that corresponds to how far out you measured your diffraction points, okay? And that is what people give you as resolution of their diffraction pattern. So if somebody tells you this crystal scattered to about 0.8 angstrom, what they mean is we measured diffraction data out to a D star that is equal to 1 divided by 0.8. Okay? So that would be, let's see, so 1 divided by 8/10, so that's 10/8, so that's 5/4. So it would be out to a D star of 1.25, okay? But it's always given in D, not in D star. What does that really mean? If you have no feeling for what that means, it's kind of a useless quantity, right? Okay, so you measured your diffraction pattern to a D spacing of whatever. Well, this example actually shows you what this means, okay? This one out here, I believe, corresponds to a D spacing of about 0.8. That is what a small molecule crystallographer will usually ask you to measure out to. If your crystal does not scatter out to about 0.8 angstrom, the crystallographer will probably tell you that you should try to find a better crystal or grow a better crystal or something along those lines, okay? Because if you have to assign atoms, you really want to have this diffraction pattern, okay? You don't want some of that other stuff. So, with that we can work. This one, not quite as good resolution. It's probably somewhere around 1.2, something like that. Okay, I don't remember the exact number. These up here, certainly not good resolution. Okay, and these we don't even have to start talking about. I think these are about 5-6 angstroms, something like that. Okay, probably. Maybe a little worse. I wouldn't want to assign atoms here, okay? If you're a small molecule crystallographer, at this point in time you're lost. You can't assign atoms there as a small molecule crystallographer. Because let's check, we have a small molecule. How many different ways could that thing orient itself? A lot. Now, those of you who want to go into protein crystallography probably won't get this type of data, okay? Very, very rarely do you get proteins to scatter that well. So you usually don't get this, where you can assign every individual atom, okay? If you got a good crystal, you may get something like this. If you have a not so good crystal, you'll be somewhere between these things. If you have a rather crappy crystal, you may have to work with something like that. Okay? A small molecule person would not even try. The protein people may have to try. And part of that is proteins sometimes just don't crystallize as well. Okay? Now, what do you think? The protein crystallographer uses data like this. Are you going to believe them? You may have a few more doubts, but it actually is possible to do something with this. So this is going to be something that tells you exactly where each atom is? No, I agree. Somebody claims they can tell you that, you don't believe them. But what do you know about your protein? The general sequence. Okay? That's very powerful, isn't it? You know the exact atomic connectivity of this whole big molecule. Okay? So that's your first advantage. Do you know anything else? If I have certain amino acids, do I know what they sometimes like to do in terms of three-dimensional arrangement? Oh, now we have a lot of knots in the classroom, right? Yeah. People know that certain types of amino acid sequences tend to form alpha helices. People know that certain sequences tend to form beta barrels, things like that, okay? Now, the combination of that knowledge with diffraction data of kind of questionable quality may actually allow you to figure out quite a bit about your protein, okay? Because you're not asked to distinguish where each atom sits. You're asked to figure out, is this an alpha helix? You probably need a lot less resolution in your electron density map to figure that one out, right? And all you're looking at is the general shape of the blobs. So you can work with much lower resolution data, making use of all your additional knowledge about your protein. But that is why you can't just take a protein crystal that you found somewhere and you know nothing about it, throw it on and solve your structure, okay? You need to know your sequence. You usually won't get atomic resolution where you can figure out what your sequence is by doing your diffraction experiment. It's not going to happen, okay? So you have advantages and disadvantages. It's just a different game. On a fiber, you usually do a very different experiment, okay? Part of that is, do you really look at a regular diffraction pattern? You usually don't, right? You folks are usually doing small angle. So what you're looking at in many cases is the Fourier transform of your objects, okay? So you will be dealing with computer programs that deal with these Fourier transforms, that use models of what does my object look like, to then go back and say, this is what I should see as a Fourier transform of that object. So it's a lot more diffuse scattering in the background, okay, that comes from non-periodic functions. That's certainly one that requires a lot more understanding. In a simple case, if you have a small molecule, very good crystal, shoot, you push the button, you accept all the defaults, you will get a structure, okay? Whether that is a perfect structure, you can only judge if you know some crystallography. But you'll probably get something that is a good enough working model. If you do macromolecular crystallography, if you do fiber diffraction, you don't know reciprocal space, I don't think you'll get very far, okay? You need more knowledge for the non-trivial experiments. But this is what that resolution corresponds to, okay? Yes?
So if you get a bad resolution, how do you do the space and just make a new crystal? Or do you...
Basically, you need a crystal that scatters out to larger D stars, yes. So that could be going to a different wavelength, okay, where the crystal just scatters better. It could be making a new crystal, could be working at a different temperature. All of the above could change that.
Could you break up the macromolecular protein and try to crystallize the parts?
If you have a protein complex, yes, you could try to crystallize the parts. But if you have a single protein, it still usually won't give you this resolution, okay? Because there's just enough floppiness, enough disorder. And let's check. We talk about infinite crystals, right? If we have a unit cell that is 5 angstrom on edge, we got a crystal that is, let's say, 100 microns. Okay, how many unit cells do we have in there? A lot, right? I mean, basically we have about 20,000 unit cells. It's not infinite, but it's approaching it, right? You got a macromolecule, you got a unit cell that is like 100, 200 angstroms, okay, something like that, in a really big protein. Let's say 100 angstrom, makes it easier. And let's assume you can't really grow the big crystals, which sometimes happens, right? So already you're down in the factor of unit cells. You may be working with somewhere 500, 1,000 unit cells, if life isn't so good. So you already get resolution issues from that, because your envelope function changes, right? So that's one thing. The other thing is, proteins move a little bit, right? There's a big difference between an ionic compound like NaCl. Those atoms sit pretty well in their positions. And a protein. A protein is a flexible molecule, okay? And as we talked about with the thermal vibration of atoms, if the atoms are slightly displaced in neighboring unit cells, diffraction will be slightly out of phase, right? Now imagine you're not just talking about one atom displacing it, but some loose end of that protein displacing it. It's going to be a much larger movement. It's going to be much more out of phase, okay? So that part of your electron density will just be very ill-defined. Which is another part of those. You sometimes hear people talk about this is the main part of the protein. We don't know what that C-terminus or the N-terminus is doing, okay? The reason for that is that it might just be some loose end that is flopping around, or you might have heard them talk about some loops that they couldn't find, okay? The reason for that is, if you don't see the electron density for it, you don't know where it is. You know you're lacking a certain sequence of amino acids, but that's about it, okay? So it's a very different game, and that is why there is a separate class on macromolecular crystallography at University of Toledo, okay? That is where you learn all those extra things you need to know and all these approaches that you need to take, and it goes with a lab, a full semester lab, where you learn how to handle your data, how to grow the crystals, how to do all these things, okay? But this is your first glance at what crystallographers usually talk about, like everybody in the world knows it. And that was actually the last slide in that presentation, okay? So these are the Fourier transforms. And it'll take some time to digest, trust me. I mean, there's no way around taking time to figure out what they are doing. Any questions about Fourier transforms or any of the material we've covered to this point? Right, if there are no questions, I think we can actually end the video, okay? I did bring